welcome back to this second half of today's lecture. Now I will prove the next theorem of Cohen-Seidenberg, that is called, so let us write it as a theorem now, theorem. This is called going up theorem. So also it will explain, the statement itself will explain why is it called going up theorem, and there should also be going down theorem. So we will come back first to the going up theorem. So as usual we have B, this is integral extension, of rings, and given prime ideals where P contained in Q. These are prime ideals in A. Both these are prime ideals in A, and one is contained in the other. And we have seen that lying over theorem, I can certainly find P prime in spec B such that this P prime is lying over this P. That means this P is A intersection P prime. This is going up, this is lying over theorem. Now we also know there is a P double prime, which, or Q prime. We also know there is a Q prime in the spectrum again, which lies over this, but we do not know whether we can choose P prime is contained in Q prime, and the answer is yes, we can choose Q prime which lies over Q and this contained here. So this is very important. So that is precisely, so then I will write the statements, then there exists Q prime with Q, not Q prime, P prime. P prime contained in Q prime and Q prime intersection A is Q. So what is given? Given P prime with P prime lying over P, we can find Q prime which is lying over Q and P prime is contained in Q prime. So it going up, and this you can keep gradually going as long as, if you have given a chain of prime ideals below in the ring and lying over theorem you choose one which is lying over P, then by going up theorem you choose one lying over this, and so on. That is why it is called going up theorem. Alright, again the proof is very simple. Proof. Now earlier we have, what we have done is we have localized. Now we have to go modulo because we want somebody contained in this. So B, A is here, this is integral, and we have given P and given P prime. So let us go mod P prime, B mod P prime, and this one will contain A by P now because P is A intersection P prime. So this is also inclusion and this is also integral, this we have noted earlier, and now this is a residue class map, this is also residue class map. Now here this Q by P is a prime ideal. This is in the spec of A by P, because spec of A by P is precisely those prime ideals of A which will contain P, and Q is one of them. And lying over theorem will tell you there exists Q prime, a prime ideal, Q prime in this ring by P prime in the spectrum of B by P prime. So there exists this which will lie over this. So which will lie over this. So that means this is lying over this. This means this prime ideal is precisely this Q prime by P prime intersected with A by P is equal to this one, Q by P. But what does this mean? This is a prime ideal. Here means now when I pull it back to the ring A, ring B, this P prime has to contain Q prime. So P prime is contained in Q prime, and then this one is lying over P, and then this you come this way, this will lie over Q. So we achieved this by going modulo. So that was more simpler than probably the lying over theorem. So this is going up. So this going up theorem will say that this will tell us, I will just remark here, I do not have much time to elaborate on this. So remark says here that if A contained in B, extension integral extension of rings, then dimension of A will be equal to dimension of B, where dimension of the ring A means supremum of R in N such that there exists a chain P0 contained in not equal to not PR. Then the dimensions are equal, because whenever you have a chain down, you can keep, by going up theorem you can extend the chain to the ring B, and whenever you have chain up, by contracting it you will get a proper chain, because no time there will be equality in between. So this is what the consequence of this. Unfortunately I cannot spend more time on this. This is called a crude dimension of the ring A. Just to give a flavor, what is the dimension of a field? Dimension of a field is 0, because there is only one prime ideal, namely 0, and the moment you go on, then it will not be prime ideal. Dimension of a k polynomial x, that is just 1, because 0 is one prime ideal, the next prime ideal is x, is not equal, and every non-zero prime ideal is maximal, because this is a PID. Therefore the length cannot have more than 2 elements in a thing. This is more, so in particular dimension of a PID is also 1. And now dimension of the polynomial ring kx1 to xn, one can prove this is n, and this will match with our usual earlier study that we have seen. If you look at the vector space k power n, this is a n dimension of k power n, and the k vector space is n, and this corresponds to the affine space. So this corresponds, in our situation, this corresponds to the spectrum of kx1 to xn. So it matches with that. And to prove this, and also to prove more generally, we will be interested in proving if A is a K algebra of finite type, then how do you write down what is the dimension? By the way, here from this definition it is not even clear that this dimension is finite or not, because it is supremum over the chains in spectrum. Who knows, the chain may go on for longer and longer, and we do not have any clue how does one prove this statement. But this is how do you compute for finite type algebra over a field. K is a field. This is interesting, and this is very important. In fact, it is very important that the algebraic geometry really starts from such things. We will match over this. Now, two more things I wanted to say, namely one, what do you do with a finite algebra, finite type algebra over a field, and how do you compute the dimension? That is one. And secondly, as I mentioned, going down, going up and going down. So, let me state going down first. I will not prove it, but let at least a statement we will do it. So, going down is let A contained in B be an integral extension of integral domains. Now, we have to assume this is integral domain, both are integral domains. This is added extra. So, I will just note what we have added extra assumptions. And also we need to assume, suppose that A is a normal domain. That means A is integrally closed in its quotient field. Then the going down holds. Then what is going down? So, B is here, A is here. So, now given P1 contained in not equal to P2, suppose I have given P2 prime ideal in B such that this lies over this, then we can go down. Then there exists P1 prime which is contained in equal to this, and then this lies over this. This is what the statement is. Then you can go down. But this has two extra assumptions. Then the going up didn't have any assumptions. The only assumption we had was this is integral extension. This is integral, that was what given, and then this is normal, both are domains, and this one is normal, integrally closed in its quotient field. Both the assumptions are very important, and I will not be able to prove this because our time is coming to end, but I will close this course with a very important statement which will tell us how do you compute the dimension of a finite type algebra over a field, and that one is very important theorem. This one is called Noether's normalization lemma. There are I am going to state only the classical version. So, K is a field and A be a K algebra of finite type. That means what? So, that is A is a quotient of polynomial algebra in finitely many variables over the field K, modulo sum ideally. That is typically an algebra of finite type. It is algebra generated by finitely many elements. It may not be finite finite K algebra. It as a module it may not be finitely generated. All right, then there exist D elements y1 to yd. Let me call small one y1 to yd in the ring A such that 1 y1 to yd are algebraically independent over K. So this means, that is they are, if I take the subalgebra of A generated by y1 to yd, this one is isomorphic to the polynomial algebra. This is polynomial algebra. That means they do not satisfy any non-zero polynomial with coefficients in K, then such elements are called algebraically independent elements. And second, so here A is integral over the subalgebra generated by y1 to yd. This is a sub of that because y1 to yd are, this is A subalgebra of A generated by this y1 to yd. So because of this 1 and 2, we know that this is the integral. So whatever the dimension of A, what we are looking for, that will be dimension of the polynomial algebra. So somehow if you would have proved dimension of the polynomial algebra is D, the number of variables, then our problem for the finite type algebra is also solved. Alright, so I will not have much time to prove this, but I would strongly recommend when you want to study further from this course, you should look at, so continue with commutative algebra course on NPTEL. This was from January to April. This was recorded under IIT Bombay. This course in fact starts with Noether's normalization lemma. I forgot to say that this was due to Noether. I said in the title, this is Noether's normalization lemma. This is also short abbreviated as NNL. So this course starts with that, and further it goes to commutative algebra and more into the homological methods in commutative algebra, which is also needed. So with this I would like to start the course, and I must confess that there is not much algebraic geometry is done in this course. It only started because Hilbert-Null-Stranzas was the cornerstone that we have proved it, and not only we approved it, we approved many equivalent versions. So this should give participants more courage to learn more abstract algebraic geometry from many books which are written this way. And of course commutative algebra will be very important, and time to time it will need upgradation to study algebraic geometry. With this I will stop, and thank you very much.